It is 6:18 on a cold Monday morning. You are the senior rail control manager, responsible for a commuter line carrying thousands of passengers into the city. Suddenly, Service 214, a train carrying 620 people, vanishes from your tracking screen. The driver radios in to report that everything appears completely normal. There is no emergency. This control screen interface shows how a basic track circuit operates. When a train enters a specific zone, the system detects its physical presence, and the corresponding section of track lights up solid to indicate it is occupied. If a connection breaks, the fail-safe defaults to caution. The system immediately forces the zone to flash occupied, preventing any other trains from receiving permission to enter. But look closely at what is actually happening on the display. The occupied block drops away completely. The fail-safe has been bypassed. A small train continues to move invisibly inside an entirely blank section of track. You face two distinct paths. Choice A is a full shutdown, stopping every approaching train until technicians verify the track is clear. Choice B relies on restricted manual control, keeping trains moving slowly under verbal instructions while engineers investigate what appears to be a localized display fault. You have 60 seconds to choose. You must make a decision based entirely on this initial, incomplete data. In a high-stakes crisis, operators often build their response around what they assume to be true. They assume a system failure will trigger a protective response, relying on supposed fail-safes rather than waiting for verified facts. To verify the facts, the control room checks the electronic event log. The data records the train entering the section, then logs the track as clearing just 7 seconds later. A train traveling at permitted speed requires nearly 3 minutes to cross that distance. The system is presenting physically impossible information. This timeline flowchart compares two distinct errors. An unknown or occupied status acts as a shield, safely blocking trailing trains from advancing. A false clear actively lies. It tells the system the track is empty, directly inviting a second train to accelerate into an occupied zone. The fault is not contained to one train. On a completely separate track branch, a parked maintenance vehicle momentarily vanishes from the system, losing its occupied status entirely. Tracing the lines from both failing track sections leads to a single central hub, a cable cabinet near the junction that was recently flagged for moisture intrusion. The problem is no longer isolated to a single display screen. The consequences of stopping the line are mounting. A freight train is approaching the junction. The manual communication plan requires drivers to use their radios, but the track leads into a tunnel known as a radio dead zone. Simultaneously, senior management warns that a total shutdown during the morning peak will cause severe commercial damage. Evaluating new evidence requires a willingness to abandon your initial assumptions. You must recognize the precise moment a problem shifts from a localized glitch into a systemic failure with expanding boundaries. A technician arrives at the shared equipment cabinet. He finds standing water on the floor and active electrical arcing across the terminals. The schematic of the safety interlocking system reveals the final, fatal piece of evidence. Corrupted data flows directly from the wet cabinet into the central computer. Without any authorization from the control room, the signal for the trailing train flips from red to green. The entire safety architecture is compromised. The interlocking computer, the ultimate safeguard designed to prevent collisions, is now actively making deadly decisions based on poison data. The backups are failing together because they rely on the same corrupted source. The system is now issuing unauthorized commands. Your safety margin is gone. You must lock in your final choice between a full shutdown and restricted manual operation. A degraded system is only safe to operate if its backup protections remain completely isolated from the core fault. When the primary system and the backups share the same vulnerability, you have entered a state of uncontrolled degradation. Because that isolation no longer exists, the definitive answer is choice A. Stop the line completely until the track and signals can be physically verified. Look at this trajectory path for train 214. The driver reached the next station without a collision, clearing the danger zone mere seconds before the faulty signal turned green behind him. That successful arrival was the product of pure luck, not a safe operating procedure. This cross-section diagram exposes the illusion of independent backups. The signals, the routing computer, and the track monitors appear to these separate safety layers. In reality, they all rested on a single collapsing pillar, the wet cabinet. This list highlights the 4 psychological traps that push operators to keep moving. Normalcy bias treats rare failures as routine. Authority bias prioritizes management pressure over safety data. Confirmation bias focuses only on evidence that supports the chosen plan. And outcome bias tricks us into believing a process is safe because the result was harmless. Achieving a safe outcome through a dangerous process is a failure of logic. Rigorous critical thinking demands that you abandon your original plan the moment the foundational evidence changes. This framework applies long after you leave the control room. You see it when a car displays an intermittent brake warning, when a secure network logs unusual activity, or when a company's financial ledgers no longer balance. This layout serves as a 3-point critical thinking cheat sheet for evaluating complex failures. 1. Watch for expanding boundaries. 2. Verify your backups are truly independent. 3. Separate external pressure from actual physical evidence. Critical thinking is not about blindly choosing the most cautious option every time. It is about actively monitoring the evidence, testing your assumptions, and identifying the exact moment an isolated fault mutates into an unmanageable hazard.